All right, let's get into it. We all have computers with multiple cores these days, but have you ever really stopped to think about what's actually happening under the hood? It turns out it's this incredibly complex ballet. And in this explainer, we're going to pull back the curtain on how an OS like Windows orchestrates all that power to make sure everything runs both fast and fair.
And this is the question that really gets to the heart of it, right? You go out and buy a machine with a ton of cores, you're expecting it to be just ridiculously fast, but it doesn't always scale that way. The truth is, just having more engines doesn't automatically make the car faster if they're not all working together in perfect harmony.
And that's really the whole trick, isn't it? Raw power is one thing, but the real magic is in coordinating all those processors, managing how they access memory, and making sure every single application gets its fair share of the pie. That requires some seriously smart management.
So to really get how Windows pulls this off, we've got to look back at its roots. See, one of its core design goals, right from the very beginning, was that it had to run well on multiprocessor systems. This wasn't some feature they tacked on later, it was baked right into its DNA.
The model Windows win with is called Symmetric Multiprocessing, or SMP. And that word, symmetric, is absolutely key. It means every single processor is an equal. There's no master processor bossing the others around. Any task, whether it's from the OS itself or one of your apps, can run on any core that's free.
And this is a huge difference. In the old asymmetric model, you'd basically create a bottleneck. That master processor running the OS would just get swamped, leaving the other cores sitting around waiting for orders. The SMP model, though, is so much smarter. It creates this big pool of processors that can all just grab the next thing off a shared to-do list. That's the secret to real performance scaling.
But, this super elegant solution creates its own brand new headache. I mean, if you have all these equal processors constantly trying to access the same shared memory, the same toolbox, let's say, you get a massive traffic jam. This memory bottleneck became the next big hurdle to overcome as computers got more and more powerful.
Right, so to fix this traffic jam, the hardware itself had to evolve. But that meant the Windows scheduler had to get a whole lot smarter too. It couldn't just assume anymore that all memory was the same distance away from every processor.
And the solution is something called non-uniform memory architecture, or NUMA. The easiest way to think about it is like creating neighborhoods. Each little group of processors gets its own local super-fast memory. It's way quicker for a processor to grab data from its own neighborhood than it is to travel all the way across the system to get data from someone else's memory. So because of this new physical layout, the scheduler can't just wing it anymore. It needs a map, right? A kind of GPS for the computer's own hardware. It has to understand the geography, which processors live in which neighborhood, to make smart decisions. The old way of treating every processor as identical just wouldn't work. And the first layer of that map is something called a processor group. Windows basically lumps processors together based on which NUMA node, or which neighborhood they belong to. This is how the scheduler gets its high-level, bird's-eye view of the system. Then, inside that processor group, the scheduler zooms in even further. It uses what are called CPU sets to figure out which specific cores a particular task is allowed to run on. This creates what's called an affinity, which basically just means it's trying to keep a task running in its ideal spot. The whole goal is simple. Keep the code and the data it needs physically close together and avoid those really slow trips to another neighborhood's memory. Okay, so we've solved the raw performance problem. We've made the scheduler smart about the hardware layout, but what about us, the users? On a busy server with tons of people logged in, or heck, even on your own desktop with a dozen apps open, how does Windows make sure no single task just hogs all the power? And that brings us to the final piece of this puzzle, a system called Dynamic Fair Share Scheduling, or DFSS. This whole thing is about making sure everyone gets a fair shake and that the system stays responsive no matter how busy it gets. At its core, DFSS is there to prevent one thing: CPU starvation. I mean, think about a big terminal server where lots of people are working at the same time. The system makes sure that every user's session gets a fair slice of the processing power. That way, one person running a really heavy job can't grind the whole system to a halt for everybody else. And get this, system admins can actually tune this stuff directly. They use something called job objects to group processes together and then apply limits. A weight-based share is kind of like a flexible budget. It guarantees you a minimum piece of the CPU, but you can use more if other people aren't using their share. A hard cap, on the other hand, is exactly what it sounds like. It's a strict ceiling. It says this group of processes can never go above, say, 20% of the CPU, period.
So when you put this all together, what you've got is this really sophisticated, multi-layered strategy. It's a constant, delicate balancing act between raw speed, the physical realities of the hardware, and the simple need for a fair, responsive experience for the user.
So let's just recap the three big ideas here. It all starts with that beautiful SMP model for pure scalable performance. Then you add a layer of intelligence with NUMA awareness to keep data physically close to the code that needs it. And finally, you layer DFSS on top of all of that to make sure this immense power is shared out fairly among everyone.
But here's the kicker. This whole balancing act isn't a one-size-fits-all deal. As this quote explains, the priorities actually change depending on what the computer's for. So, Windows Server is tuned by default for raw throughput, just getting as much background work done as possible. But the desktop version you and I use is tuned for responsiveness, making sure the system feels snappy the instant you click something. It's the same core system, just with different priorities.
And that brings us right to the cutting edge, to what's happening right now. You see, everything we've talked about so far has kind of assumed that all processors are more or less equal. But the future is, well, it's a mix. We have chips now with powerful big cores and super efficient little cores side by side. So the question is, how does a scheduler handle that? Do you stick a background task on a little core to save power, or a demanding game on a big core for speed? That's the next great challenge for this amazing balancing act.
If you want to help me out, please smash that like button, leave a random comment, and subscribe if you want to become a better hacker.